Okay, so in this video, we're going to continue the fundamental set of solutions in the Wronskian. In this video, we're just going to look at a whole bunch. I think we just have 3 examples to look at. These problems are a little long, so this first one is really short, though. So, like, in the last video, we had to solve for y1, y2, right? In this first problem, we're given y1, y2. It just asks us to find the Wronskian. So now, if you recall, if we take the Wronskian of e to the 2t, e to the negative 3t over 2, we would just take the determinant of e to the 2t, e to the negative 3t over 2, and then we just take the derivatives of each, so 2e to the 2t, negative 3 halves, e to the negative 3 halves t, and that determinant is equal to, remember it goes this way first, and then this way. So that would be negative 3 over 2. What's 2 minus 3 over 2? Well, 2 is, well, if we're going to subtract it, that would be what? 4 over 2 minus 3 over 2, which is 1/2. So that's e to the 1/2 t. And then we then subtract the multiplication of these two. So then we have minus 2e to the, once again, 2, same thing, 2 minus 3 over 2 is 1/2 t. So then this will equal, well, negative 3 over 2 minus 2, it's negative 7 over 2, right? So then we're left with negative 7 over 2 e to the 1/2 t. And this is all it asked for. Now, if we were doing one of these problems full out, right, this is non-zero, so then we would have a fundamental set of solutions. But it just asks us to find the Wronskian. That means nothing to any kind of problem or anything. Okay, so now let's look at our next problem. Yeah, so remember the last video how I said that if we're given one like this, we have to solve for 2 general solutions. So let's go through the whole problem here. Let me find it in my notes. Okay, so first things first, we need to solve for y1 and y2, right? Step 1. Solve for y1 and y2. So to do that, we propose I guess in this case it would be y, right? Y is equal to e to the RT. So then we have y prime is equal to r e to the RT. Y double prime is equal to r squared e to the RT. Plug those back in. R squared e to the RT plus r e to the RT minus 2 e to the RT is equal to 0. Those cancel. R squared plus r minus 2 is equal to 0. This factors into r plus 2, r minus 1. So then r is equal to negative 2 and 1. So then we can rewrite our 2 solutions now. So y1 is equal to c1 e to the negative 2t, and y2 is equal to c1 e to the t. Okay, so now we have those. We need to now determine Like the problem asked us, find the fundamental set of solutions. We don't know if it is a fundamental set of solutions, so we have to determine if it is. So take the Wronskian of... Sorry, I should not have these C's on here, right? Not yet. Of y1 and y2. This would look like the determinant of e to the negative 2t, e to the t, negative 2, e to the negative t, right? I just took the derivative, and the derivative of e to the t is just e to the t. So now, e to the negative 2t times e to the t would be negative 2 plus 1 is negative 1, so that's e to the negative t minus negative 2 e to the negative 2t plus 1 e to the negative 1t, so it's negative t. That becomes e to the negative t plus 2 e to the negative t, which equals 3 e to the negative t. That is non-zero, so we have a fundamental set of solutions. So it wants us to find the fundamental solutions. So when it says find the fundamental set of solutions, then we have to write this out. This is what it means by find the fundamental set of solutions. So now we found them. This is our answer for this part. Now what else does it say? Specified by theorem 3.25 for the given differential equation and initial point. So right, we didn't use the initial points yet. So we have to now find the... This was a little miswording, but it just says find the fundamental set of solutions. We have to go through the whole thing and find the general solutions as well. So, what are we on? Step 3 now? General solution. Oh, we can actually write our general solution now. Right? That's just y is equal to c1 e to the negative 2t plus c2 e to the t. Okay, so now we need to look at the theorem for the IVP, right? So unfortunately, we have to do it 2 times. So we're given that t naught is 0. And we have to look at this theorem here. So y of t naught is equal to 1. And for this is for y1, by the way, for general solution 1. So we have y of 0 is equal to 1. And we also have y prime of 0 is equal to 0. So we need to solve for c1 and c2 using both. So the first of all, y prime is equal to negative 2 c1 e to the negative 2t plus c2 e to the t. For this one, we have 1 is equal to c1 plus c2. For this one, we have 0 is equal to negative 2 c1 plus c2. This one, I'm just going to use substitution because this one's really easy to use substitution with. I'm not going to go through Cramers rule for this one, but I do highly recommend using Cramers rule for some of these. As a matter of fact, I'll do this one without it, and I'll do the next one with Cramers rule, alright? So, for this one, C2 is equal to 2C1. So then we plug that in over here. 1 plus C1 plus 2C1. Oh, 1 is equal to. So then C1 is equal to, so what is that? 3C1 is equal to 1. So then C1 is equal to 1/3. Plug that back in over here, and we get C2 is equal to 2/3. Right? So then our first general solution would be 1/3 e yeah, 1/3 e to the 1/3. Oh, wait. What was our... Sorry, that's negative 2t. Plus 2/3 e to the t. That's our first general solution. In the next one, we need to use our other initial conditions. So now we look over here, we have y of 0 is equal to 0. So we just flip what's on the right side there. And then we have y prime of 0, sorry, is equal to 1. So for these cases, we have 0 is equal to c1 plus c2. And for this one over here, we have 1 equals negative 2 c1 plus c2, right? So this one's really easy to solve with substitution once again. Let me add a page. So we can easily solve, so c1 is equal to negative c2. So then that's 1 is equal to positive 2c2 plus c2. 3c2 equals 1. c2 is equal to 1/3. If c2 is equal to 1/3, we know c1 is equal to negative c2. So then c1 is negative 1/3. And then we just write out our next thing. So that's y2 is equal to negative 1/3 e to the negative 2t plus 1/3 e to the t, right? And this is our second general solution. Now really quickly, I just want to redo this section with Cramers rule, just to show you. Because once again, it is important to get familiar with Cramers rule, because we will be using it a lot when we get to variation of parameters. So let's look here. So if we have, right, this is from the last one. So let me flip these. So for Cramers rule, to solve for C1, remember it's a determinant over a determinant, and for C2, it's a determinant over a determinant. Now this is Cramers rule is pretty fast. Once you get the hang of it, you can do it really fast. I mean, really fast. But you see how substitution's really easy though. But so it'll save you so much time later on when we get when. So I would recommend trying it. Just trying it. Do it first. See if you remember what the way it goes. So the denominators are both the same for both. So this is 1, 1, negative 2, 1, right? We just look at this part here. The coefficients. Once again, 1, 1, negative 2, 1. Now for C1, remember, we're looking at this section, but we're looking at it backwards. So it's going to go 0, 1, 1, 1. And for C2, we're looking at this section right here. So it's 1, negative 2, 0, 1. And then from there, we just do our determinants. So this would be, that's 0 minus 1 over 1 plus 2. This would be 1 minus 0 over 1 plus 2. right? So then our C1 is negative 1/3, and our C2 is equal to 1/3. And if we look back up here, C1 is negative 1/3, and C2 is 1/3. So you can see how once you get the hang of Cramer's rule, it can be really fast to use. And it's very systematic. It's a lot more straightforward than substitution, in my opinion. It's just memorizing, which way the numerators go. That's about it. But once you learn it, it's pretty simple. Okay, one more example. So 19. Let's see. Verify that the functions, so they give us y1 and y2 already, right? So this is really simple. We don't have to find any general solutions. All we have to do is verify that y1 and y2 are solutions of the given differential equation. So I'll tell you right now exactly how to do this. So I'm going to show you a really cool trick. So let me rewrite these. Okay, so let's look at y1. Okay, so if you look at y1, take the first derivative. Oops, I'm sorry, first and second derivative. This would become negative 2 sine of 2t. This would become negative 4 cosine of 2t. Let's do the same thing for y2. So for y2, we have sine of 2t. y2 prime would be 2 cosine of 2t. And y2 double prime would be negative 4 sine of 2t. Now, to prove that they are a solution to the given differential equation, the first part is this. We have to plug these back into here. So if we plug those back into here, we have negative 4 cosine of 2t plus 4 times y, which is cosine of 2t. And guess what? These are the same, different opposite signs. We're left with 0 equals 0. Right there, that proves that y1 is a solution of the given differential equation. For y2, let's do the same thing. We have negative 4 sine of 2t plus 4 sine of 2t is equal to 0. Once again, same thing, opposite signs. 0 equals 0. y2 is also a solution of the given differential equation. Now the second part, do they constitute a fundamental set of solutions? Well, let's take the Wronskian. The Wronskian of, we have cosine of 2t and sine of 2t. So remember, the Wronskian is just the determinant. It's cosine of 2t, sine of 2t, over 2. The first derivative of that is 2 negative 2 sine. It's negative 2. Yeah, negative 2 sine of 2t. And this one is 2 cosine of 2t. Take the determinant. This would become 2 . That's just cosine squared, right? Yeah, so 2 cosine squared 2t. Yeah. Minus, but we have this minus here, so that becomes plus 2 sine squared of 2t. And this is a identity, right? So remember that this plus this is 1. So if you take the 2 out, you have cosine of squared of 2t plus sine squared of 2t. This is 1, so then we're left with 2. So the Wronskian is equal to 2 of, I'll just write down y1, y2 is equal to 2. It is non-zero, so then we have a fundamental set of solutions. And I believe that's all this problem asked for, right? And that's it. So I hope you enjoyed the video. If you want to see like another example where we don't have to use, where they give us the initial conditions, we don't have to use this theorem, go back to the last video and I did an example with Cramers rule, of course, showing how to do it when they just give you. It's the same thing. You do the same exact thing. Just you don't need 2 general solutions. You only need 1, right? All right. Hope you enjoyed the video. In the next video, we're going to be looking at, let's see. We're going to be looking at complex roots in the next video.